This section is about arithmetic in the Hindu-Arabic system, and that is our number system. So this is going to look somewhat familiar, but there's going to be components of it that will look a little different as well. The first thing I need to talk about is what expanded form is, and we've alluded to it several times in the last two sections looking at other number systems. But what this really is the form in which the value of the digits in each position is made clear. For example, 942 is 900s, 4 10s, and 2 1s. So we can either write it in words, or we could also write it as sort of like 900s as 9 times 100, and 4 times 10, and 2 times 1. And when we talk about writing these in expanded form, that's more of what we're generally thinking of, is writing out the form of it in terms of the actual numerical numbers, not necessarily the words. So for instance, this 1 right here is actually 1 times 10,000. And we have 2 times 1,000. We have 3 times 100. There's 9 times 10, and then there's 8 times 1. And another thing that your book will sometimes do, and I want you to be aware of what's happening, is that they'll actually write these in powers of 10 instead of just the values next to them. So instead of saying 10,000, it would say 10 to the fourth. And a good way of remembering which power it is that you're on is that you can count the number of zeros. There's 4 zeros in 10,000, so this is 10 to the fourth. There's 3 zeros in 1,000, so this is 10 cubed. There's 2 zeros in 100, so that's 10 squared. There's 1 0 in 10, so this is 10 to the first, and then we've got 8. And this is an awkward way of writing it, although it's 100% accurate. We can write 1 as 10 to the 0. All right, so just like we can take this and we can write them in expanded form, we can also take what's in expanded form, like on example 2, and we can write it simplified. So when you see the 10 times, or the 5 times 10 squared, 10 to the fifth, excuse me, that's 5. It's just in the 100,000th position, because a 10 with 10 to the fifth power is a 1 followed by 5 zeros, which is actually 100,000. We've got a 0 in the fourth position right here. Then we've got a 3 in the thousandths position. There's a 5 in the 100th position, a 6 in the 10th position, and then an 8 in the ones position. So we've got 503,568. All right, so the distributive property is a property of algebra that you have used many times before. You actually encounter it much earlier than this when you're working with what will later become algebraic expressions, and we're sort of going to think of it backwards. If we have b times a and c times a, we also could write this as b plus c times a, and we usually think of the distributive property as starting on the right-hand side and moving to what I've currently written on the left, but it works both directions, and this works for all real numbers a, b, and c. And the reason we're doing that is because of how we're going to think about adding and subtracting in expanded form. So we're going to take 75 and 34. So in expanded form, 75 is actually 7 times 10 to the first, and then 5 times 10 to the 0. And 34 is 3 times 10 to the first, and 4 times 10 to the 0. And in reality, what we're doing is we're saying that we can add these together. And notice you've got 5 and 4, and they're both times 10 to the 0, so this could actually be written as 5 plus 4 times 10 to the 0. That's the distributive property at play there, and it's moving from left to right. We've got two numbers, each multiplied by 10 to the 0, and so we can add those numbers together. And we can do the same thing for the 7 and the 3. So 7 times 3 7 plus 3 times 10 to the first. Now, awkward things, of course, happen here a little bit. Here's 9 times 10 to the first, 10 to the 0, excuse me, and of course that's fine. But the part that's awkward is this one, because 7 plus 3 is actually 10, and 10 is not a numeral, it is actually two numerals, 1 and 0. And so you want to remember that 10 times 10 is actually a 100. So this is actually 1 times 10 squared. And then we have 0 times 10 to the first. And then we have our 9 times 10 to the 0. And of course, written in condensed or simplified form, this is 109. And you could verify that very quickly if you added 75 and 34. Just sort of as you remember adding them, you get 109. And we can subtract in much the same way. So we'll write this as it appears in expanded form. So this is 7 times 10 to the first plus 4 times 10 to the 0. And then we subtract, and we have 4 times 10 to the first. And then I have plus, and this is all subtracted, plus 8 times 10 to the 0. And we run into a problem because we can't actually subtract 8 from 4, right? So we have to borrow. And the way that we borrow is that we actually are going to take one away. So our idea is that we're actually going to rewrite that first line as 6 times 10 to the first plus 14 times 10 to the 0. In other words, we're going to borrow that one. And then we can subtract 4 times 10 to the first and the 8 times 10 to the 0. So we have 14 minus 8. Remember, the minus is on the outside here, right? So this is applying towards everything inside, so it's all subtraction. So 14 minus 8, which is 6, times 10 to the 0, and then 6 minus 4, which is 2, times 10 to the first. So we actually have, in condensed form, this would be the number 26. Now, an old way of doing mathematics was, or mathematic manipulative, was something called an abacus, and this is kind of like the oldest methods for speed calculating. So let me tell you some details about an abacus. The first one is that one. This is one of the oldest ways for speed calculating. And the idea is this, that the beads toward the middle I'll call it the middle rod, are active. And others are ignored. Also along this lines is that the beads above the rod are worth 5 times the value of beads below the rod. And this is expressing these things as powers of 10. So each rod is a power of 10. And it's like what we do when we write our number system with the largest power on the left. All right, so this example is actually from page 172. So if you want to take a look at page 172 in your textbook, what you see here is you actually see the powers. So this is 10 to the 0. This one's 10 to the 1. Here we have 10 squared, 10 cubed, and then 10 to the 4th. So again, it's told us that the beads above the rod are worth 5 more, and the beads that are sort of pushed toward the middle count, and the others don't. So let's actually just start on the far left, and we can count The bead above the rod is pushed away from the rod. There's 3 beads below the rod that are pushed toward the rod. So they each have the value of 1. So this is the number 3 on the first rod. And that rod is 10 to the 4th. The next rod has 1 bead below pushed toward the rod. So that's worth 1. And there are no beads above the rod that are pushed toward it. So that's worth 1. And that's 1 times 10 cubed. Plus the next one, let's see, we have 2 beads below pushed toward it. So that's 1 and 2. The bead above the rod on this middle rod as well is also pushed toward it, and it's worth 5. So this is actually the number 5, 6, 7 times 10 squared. And then we have all the beads pushed away from the rod on the 10 to the first one. So that's 0 times 10 to the first. And then our last one is actually 1 bead above, worth 5, and 1 bead below, worth 1. So this is the number 6 times 10 to the 0. And again, if we were to write that in condensed form, this is 31706, or 31,706. Okay, so we're going to do the same thing again. I'm going to get you another example. And one of the things that we need to make mention of real quick is that you notice there's always 1 bead above the rod, and there's always 4 beads below the rod. And I mean, what you have to imagine in your mind is that an abacus is a physical object. It actually exists. Those beads are stuck on rods and they move up and down, they slide, but they don't have sort of this property that we can kind of take beads off or add extra beads. That's never happening. We're always having 1 bead above, either pushed towards the center or pushed away, and 4 beads below, either pushed towards the center or pushed away, or some combination thereof. So this first one right here, you notice everything is pushed away. So this has the number 0, but then again, so does the next one. Everything's pushed away, it's 0. The third one has 2 beads below the rod pushed toward it, so this is the number 2. This fourth rod, moving from left to right, has 1 bead above, which is worth 5, and no beads below pushed toward it, so this is worth 5. And this last one right here has the 1 bead above, worth 5, and 1 bead below, worth 1, so this is number 6 pushed toward the rod. So in expanded form, we could write this as 2 times 10 squared, plus 5 times 10 to the first, plus 6 times 10 to the 0. And if you want to identify that in condensed form, that's the number 256. Now we're going to do the same kind of thing, but we're going to go in reverse. We're going to be given a number and we're going to sketch the abacus for it. All right, so in sketching my abacus, I draw sort of a grid box with a line in the middle. I need 5 vertical bars. There's 3, 4, and 5. Okay, so every rod has 5 beads on it. Okay, 1 above, 4 below the rod in the middle. So this is the number 7. So the way I get the number 7 is by getting a number above worth 1 and 2 numbers below worth 1. So 5 above, 2 below, worth 7. But I used to have 4 below, which means I need to add 2 more beads right there. And I'm going to try this with a circle. Let's try it this way. Let's see. Oh, that's a little bit too wide. Let's make my circle a little bit thinner. That'll work. All right. So I've got 1 bead above, 2 beads attached below, and then 2 beads at the bottom below. All right. Now I've got the number 0. Well, the number 0 means everything is pushed away from the center rod. I still have 1 above the rod, but it needs to be pushed away. And I still have 4 below the rod, but they also need to be pushed away from the rod. So there's my 4 here. All right, so the number 1 means I have 1 bead below the rod active. So the 1 bead above the rod needs to be pushed away because it is inactive. And then I have 3 beads below the rod that are also inactive. All right, so my next one is the number 6. I get the number 6 as being 5, which is 1 above, plus 1, which is 1 below. And I need 3 more beads below the rod, so there's 3 in the bottom. And then I have the number 3. Well, the number 3 is 3 beads below the rod active, which means 1 bead below the rod is not active, and the bead above the rod is also not active. So this would be the abacus diagram representing 70,163. All right, there's one more topic in this section, and that is the topic of lattice method for products. And the lattice method for products is a very interesting idea. You know lots of ways probably you've seen ways anyways of multiplying. This is not one that you probably were taught when you were in elementary school, but it is one that is now being taught in elementary school. So I want to show you this, and it's very interesting. The way you do this is you create rows and columns for your digits. You divide each box diagonally. You compute each product and add along the diagonals from right to left. And the easiest thing to do to explain this is to actually show you one. So we're going to do 23 times 187. So the first thing you do is you create a grid box. And I need a box that will be, let's see, 3 wide for the number 187. And it doesn't have to be 3 wide, but either 3 wide or 3 long. So I'm going to make it 3 wide and 2 long. So I'm getting this grid box. So this is 1, 8, 7, 187, and then 23. And those values always go along the top and along the right. Always. They never go anywhere else. Don't put them on the left, don't put them on the bottom, top and right. And then what we're going to do is we're going to take each of these boxes and cut them in half diagonally. Okay, so and that's what's creating this lattice that the description is used, right? Lattice method. And then within each box, we're actually going to do plain old multiplication. Okay, so I'm just going to start on the top right-hand corner. You can start wherever you want, it doesn't matter. But I'm going to start with the 7 and the 2. So 7 times 2 is 14, which means the 1 goes on the top corner and the 4 goes in the bottom corner. And then 8 times 2 is 16, so the 1 is on the top and the 6 is on the bottom. And then 1 times 2 is just 2, so we just put a 2 on bottom. If it helps you, you could put a 0 on the top corner, but you certainly don't have to. We're going to go again from right to left just because it sounds like fun. We're going to do 7 times 3, so that's 21, so the 2 goes on top and the 1 goes on bottom. 8 times 3 is 24, so the 2 goes on top and the 4 goes on bottom. And then 1 times 3 is 3. And then what we're going to do is we're going to really consider these diagonals. So I want you to really think about these diagonals as being sort of marking out a column of sorts. And we start with the bottom right-hand corner where this number 1 is down in this little bitty corner on the bottom, and we add that column together, or that diagonal together, and there's only one thing in it, it's the number 1. But as we move up, you'll see things happening differently. So I've got 4 plus 2 is 6 plus 4 is 10. Well, 10 is a 0, and then I carry a 1. Okay, so this is my 1 that I carried. So then I add 1 plus 1 is 2, plus 6 is 8, plus 2 is 10, plus 3 is 13. So I'll write down my 3, and again I'll carry the 1 for the 13. And then I have 1 plus 1 plus 2, which is 4 in that diagonal spot. So my solution to this multiplication problem are the 4301 that I get on the bottom. So this answer is 4301. And of course, how many different ways could you check this? Well, you could check it with your calculator, you could check it with the standard method for doing multiplication that you're aware of. You could check it with a partial products if you're familiar with that. There's lots of ways to check and make sure that you've got the right solution for this. So we're going to do one more example, and in this example we're going to do a 3 by 3. So when I create my grid, I actually need it to be 3 long and 3 wide. So I need a little bit bigger of a grid than I just had for a moment ago. Let's try that again, because it needs to be 3 wide. So I'm going to create, and we'll use lines this time actually. We're going to create 3 rows and then 3 columns, and then we're going to divide them in half diagonally. Okay, it isn't perfect, but you've got the right idea, I think. And then, let's see here. There we go. We're going to put, it doesn't matter which number goes where, so I'm just going to go with 912 on top. and then 483 on the right. And you could do it reverse of that, of course, and it would work just fine. But all right, so let's just start in the top left-hand corner for kicks this time. So we've got 9 times 4. 9 times 4 is 36. So we're going to do a 3 on the top and a 6 on the bottom. 1 times 4 is 4, so I'm going to do a 4 on the top, on the bottom, and you can put the 0 on top if you'd like. And then 2 times 4 is 8, so there's an 8 on this one. Now 9 times 8 is 72, so there's a 7 and a 2. We have 1 times 8, and that's 8. And I have 2 times 8, and that's 16. I have 9 times 3, and that's 27. I have 1 times 3, and that's 3. And then I have 2 times 3, and that's 6. And then, again, I'm going to use the colors just to kind of further accentuate for us what we're adding up here very quickly. So you're seeing this in the bottom right-hand corner is a 6. This is a 6. You're seeing a 6 and a 3, which is a 9. You're seeing 8 and 1, which is 9, plus 8 is 17. 17 plus 7 is 24. So this is a 4, and then we carry the 2. So that's my first carry in this one is the 2. So the 2 comes up right here. So now I've got 2 plus 4, which is 6, plus 2, which is 8, plus 2, which is 10. So there's a 0, and I carry my 1. I have 1 plus 6, which is 7, plus 7, which is 14. So I write down the 4. And I carry a 1, and then I have 1 plus 3, which is 4. So my solution, again, is along this outside corner. That's why I don't want my original 912 or 483 on the bottom or on the left, because that's where my sum is going to go when I'm done. And the sum, when I'm done, is actually the product of the original problem, which is 440496. And again, you could check this in any number of ways, even besides the back of the book, to make sure that you did it correctly. But if it says use the lattice method, I expect to see the lattice method, including the grid and all the individual boxes filled in and the summations and so forth. And that's the end of the lesson in section 4.3.